Welcome back everyone. Let us actually summarize what we have done so far in character theory. So, let me recall the statements that we have proved so far. So, as before we just assume G to be a finite group and so on. So, let me just rewrite everything. So, we take G to be a finite group and we denote small c by the number of conjugacy classes of C, conjugacy classes of G. So, we also denote small s by the number of irreducible characters of G, the number of irreducible characters of G. So, with this notation, so we proved the following. So, here is the theorem. So, the theorem actually consisting of many different statements, but anyway all the statements you can call it as part of the character theory. So, what is the first statement? The first statement asserts that the number of conjugacy classes is exactly equal to the number of irreducible characters. So, that means C equal to S. So, in other words, this also counts the number of non-isomorphic irreducible representations. So, this is also equal to the number of non-isomorphic irreducible representations of G. So, this is the most important result that we have proved. So, in order to prove this, we established that the set of irreducible characters, they form actually orthonormal basis of this space of class functions. So, that also one can state it as part of the theorem. Anyway, with this observation, we also proved that any two given finite dimensional representations of G, they are isomorphic if and only if they have same character. So, two finite dimensional representations of G, they are isomorphic if and only if they have same character. They have same character. So, in other words, we can say that the characters of a given representation determines the representation up to isomorphism. The third statement, in terms of inner product, we can give characterizations for irreducible representations. So, we say a representation rho, let us say with the character chi. So, this is irreducible if and only if we take the inner product chi with chi, that is supposed to be 1. So, recall that the inner product defined on the space of complex valued functions on G. So, maybe let me just quickly recall here. So, recall if we consider this space of complex valued functions from G. So, then given any two functions f1 f2 from this space, the inner product f1 f2 is defined to be this average sum. So, you divide by cardinality of G, then the take summation f1 of G times f2 of G bar, where G runs over all G. So, this is the inner product. With respect to that inner product, whenever we deal with the irreducible characters, we get the inner product to be 1. As a fourth statement, we see that the cardinality of G, that has very close relationship with the degree of irreducible representations. So, if we denote Ni by the degree of chi I for all 1 to S. So, then we proved that the cardinality of G is exactly given by summation Ni square, I range from 1 to S. So, this is indeed a consequence of the results that we proved. So, in particularly we also have this trivial one dimensional representation. So, that we can count it as the first irreducible character. So, n 1 let us assume to be 1. So, this is exactly the one dimensional irreducible representation. So, this is just one dimensional trivial representation of G. Okay. So, this is how we set the notation. So, this is exactly the degree of chi 1. Okay. So, all these are, as I said, consequence of this very important result that we proved. So, if we take the corresponding irreducible characters, the set of irreducible characters of G. So, this form an orthonormal basis of the space of class functions. So, this form an orthonormal basis of the space of class functions. So, this is exactly this, the space of class functions. So, in particularly we can see that the rows of the character table. So, that those rows are actually orthonormal. So, recall, so what is the character table? So, here let me just recall the character table. So, we take characters as rows and then conjugacy classes as columns. So, we have let us say C 1, C 2 etcetera C s. So, these are nothing but conjugacy classes, and then we take the irreducible characters in rows chi 1, chi 2 etcetera chi s. So, then the entries are nothing but the values of these characters evaluated on these different conjugacy classes. So, we have chi 1 of C 1 etcetera chi 1 of C s and so on, chi 2 of C 1 etcetera chi 2 of C s and so on. So, that means if you rewrite the fact that chi 1 etcetera chi s they form an orthonormal basis, we can easily see that this is same as saying that the rows of this character table, they are indeed orthonormal. So, if we rewrite this result, we see that the rows of the character table, they are orthonormal. So, similarly, what one can prove? One can prove that the columns of the character table also form an orthogonal set. So, that is actually something new. So, the columns of the character table that also form an orthogonal set. So, what does it mean explicitly? So, if we actually take C, C dash to be conjugacy classes of G, and then let us take G and H to be representatives from C and C dash. So, let me state it very explicitly. So, let us take C and C dash, these to be conjugacy classes of G, and then we fix the representatives G in C and then H in C dash. So, fix these elements. So, then if we actually evaluate the following column values. So, take summation chi I of G times chi I of h bar I range from 1 to s. So, then this is exactly given by the cardinality of G divided by cardinality of C whenever C equal to C dash and 0 otherwise. That means whenever C is not equal to C dash, we get the value 0. So, this actually tells us that the columns of the character table that forms an orthogonal set. So, it is not orthonormal because we are getting this value cardinality of G divided by cardinality of C whenever we take G equal to H. Okay, so let us prove this. This is something we haven't proved yet. So, this actually immediately implies that the character table is indeed invertible. So, using this we can see that this is indeed invertible matrix. Okay, so here is the proof. Again, the proof is not very complicated. It again uses the fact that this chi 1 etc. chi s, they form an orthonormal basis of this Z of C G. So, note that we have this chi 1 etc. chi s. So, this form an orthonormal basis of this Z C G. So, in particularly given any element of Z of C G, you can write it as linear combination of chi I, where the coefficients also has very explicit expansion with in terms of the inner product of that element with this chi i's. So, given any f, given any f in Z of C G, so we can write f as summation inner product f chi I times chi I. So, this immediately follows from the fact that chi i's form orthonormal basis of this Z of C G. So, in particularly what we are going to do, we are going to apply for f equal to delta C dash. So, recall that delta C dash is the class function that takes value 1 on C dash and then 0 otherwise. So, delta C dash defined to be, so this is exactly equal to 1 if C equal to C dash and 0 otherwise. So, now in particularly we can write delta C dash as linear combination of chi i's with the coefficients inner product delta C dash chi I. So, let us write it and then expand it. So, for this G that we have fixed G in C, so we have delta of C dash of G. So, this is going to be exactly equal to given by summation the inner product delta C dash comma chi I and chi I of G. So, for I range from 1 to s. So, this just follows from the fact that delta C dash can be written as linear combination of chi i's. So, now if we rewrite what we have here, so this is can be rewritten as follows. So, this is exactly given by summation x in G delta C dash of x and then chi I of x bar. So, if we plug in this part in the summation, then what we get exactly delta C dash of G equal to summation I range from 1 to s. And so, yeah, I have forgotten this 1 divided by the cardinality of G. So, that factor also we need to keep it here, 1 divided by the cardinality of G summation x in G. Then we have delta C dash of x, chi I of x bar and then chi I of G. But note that so this particular function delta C dash of x, that is going to be exactly 1 or 0 depending upon whether x is in C dash or not. So, if we use that then we get the following. So, we can rewrite everything and then we get delta c dash of g equal to summation I range from 1 to s 1 divided by the cardinality of g summation x in c dash and then chi I of g and chi I of h bar. So, the same thing we have rewritten. So, for this it takes value 1 whenever x is in c dash and then this value we just kept it. So, I should use x here. Anyway, so the value of chi I of x is same as chi I of h. So, I can use h here, not a problem. So, note that chi I of x is same as chi I of h as x is in c dash. So, chi I is nothing but class function. So, they take the same value. So, now if we actually take out, so this is a constant function. So, then it gives us exactly the following summation I range from 1 to s the cardinality of c dash divided by the cardinality of g times chi I of g chi I of h bar. So, which is exactly equal to cardinality of c dash divided by cardinality of g summation I range from 1 to s chi I of g chi I of h bar. So, this is the value that we wanted to compute from the beginning. So, we just proved that this value is equal to delta c dash of g. So, that means, so this value is going to be exactly equal to 1 if g is in c dash, which is equivalent to c being equal to c dash, 0 otherwise. So, this proves that the sum of the values that we were interested in satisfying what we wanted. So, this is indeed true. So, this proves that the columns of the character table matrix, that is orthogonal set. So, we have proved actually rows form orthonormal orthonormal set and then the columns form orthogonal set. So, in particularly the character table matrix, that is indeed invertible. So, let us record it. So, what we have proved tells us immediately that the character table matrix is invertible. Indeed, if we go back and then look at the way we have actually observed the relations between this chi I and the conjugacy classes. So, it is actually not difficult to see, maybe you can actually take it as exercise, that the character table is in fact the transpose of the change of basis matrix from the basis chi 1 etcetera chi s to the basis delta c 1 etcetera delta c s. So, the character table So, we are talking about the matrix. So, this is in fact the transpose of the change of basis So, from actually the basis chi 1 etcetera chi s, chi 1 etcetera chi s to the basis delta c 1 etcetera delta c s. So, we know that both of them actually form a basis for this space ZCG. So, if you look at the change of basis, so then the transpose of that is exactly the character table. Indeed, that is recorded in what we have proved. Okay, it is just simply an observation. So, let me record another fact about the characters. Indeed, this is about the degree of the characters. So, we will actually later prove this fact. So, here let me just put star here. So, this will be proved later. It will be proved later. So, indeed what it actually says, so if we take the degree of irreducible representations, so they always divide the cardinality of G. So, this is somewhat closer to Lagrange's theorem. So, Lagrange's theorem asserts that the cardinality of the subgroup must actually divide the cardinality of the group. So, very similar to that, we have the degree of any irreducible representation that actually divides the cardinality of G. So, even though this is a very simple looking statement, to prove this statement we have to actually use little bit of algebraic number theory. So, I will develop all the necessary results that are needed in order to prove this important result, but it will require some more work to prove this. But this actually gives much more restrictions in terms of the irreducible representations of the degree of the irreducible representations. So, we already have some important observations. So, we have observed that, so the cardinality of G should be equal to summation n I square, I range from 1 to s, and this condition 8 also tells that n I must divide the cardinality of G. So, that means these n i's cannot be very random. So, they are very much restricted, especially when we are working with some smaller values of cardinality of G. We will see that so these observation will help us to immediately determine what are all the possible irreducible representation that we can get it for the group G. So, maybe so once I prove this result 8, so then later we will use these observation in order to actually compute character table of some smaller groups like S4, S5, D8 and so on. So, but before that let us focus on proving this. But anyway, so without proving that, proving this 8, we can again determine all irreducible representations of abelian groups. So, we can do that in a minute. But before that, let me actually make this following important observations. So, I will leave it as exercise because this is something I am going to do later using all these observations that we have done here. So, the important fact is that the character table that does not actually determine the group up to isomorphism. So, what does it mean? That means we can have actually two different groups, non-isomorphic groups with the same character table. So, for example, so this is actually somewhat involved exercise. So, later once we see proof of this, I am going to come back to this exercise, but anyway you can actually think about it. So, we can have actually for the following groups Q8 and D4. So, they will have actually same character table. So, prove that the groups D4 and Q8, so they have same character table. So, that means having same character table does not mean that actually the groups are isomorphic. Indeed, one can prove something for the P groups as well. So, if we take non-abelian groups of order P cube, So, they also have same character table. Actually, there are two non-isomorphic order p cube non-abelian groups. So, they also have same character table. Maybe if I have time later, so I can focus on smaller order p groups. So, as far as p groups are considered, so if the group has order prime p, then it is cyclic, and if it is order p square, then it must be abelian. So, they actually kind of come under some simpler family of finite groups. For them, we can actually determine completely the irreducible representations of those groups. So, what I am going to do now, like, so let us actually focus more on like general finite abelian groups. So, one can use the structure theorem in order to actually get all possible irreducible representations of abelian groups. So, before that, let me make some simple observations. So, if we start with G being a finite abelian group, so then the characters are same as actually the irreducible characters, they are same as group homomorphism from G to C cross. So, that is actually easy to do, easy to see. So, from our earlier observation, we have already observed that all irreducible representations of G, they are one dimensional. So, in particularly like the number of conjugacy classes being equal to the cardinality of G actually tells us that the all irreducible representation must have one dimensions. So, if we take rho to be irreducible representation of G, finite dimensional irreducible. So, then we have a map from G to GL1 of C. So, now note that GL1 of C can be identified with C cross. So, non-zero complex numbers. So, that means if we look at the chi rho, so which is a map from G to C cross, which is a map from G to C. So, which takes G to the trace of this rho of G. So, which is same as, because we are dealing with 1 by 1 matrices. So, we can identify the trace with its actual value in the matrix. So, with that identification, we can identify the representation itself as character of that representation. So, that is because we are dealing with one dimensional representation. So, that means the irreducible characters or irreducible representation, they are exactly group homomorphism from G to C cross. So, the home G C cross, so they are the irreducible characters of G. This is the set of irreducible representations of G, because all the irreducible representation, of course, finite dimensional, they all have one dimension. So, in particularly we can identify them with character, and they are nothing but group homomorphisms from G to C cross. So, this is the identification that we do whenever actually we talk about abelian groups. So, with this identification, so we will be able to completely determine what will be the set of irreducible representations of G. Indeed, we are going to prove that. So, G is going to be isomorphic to this G hat. So, which is, we call it as the dual group, and we are going to actually define group operation on this set, that is given by pointwise multiplication, and then later prove that G is indeed isomorphic to G hat. So, I will actually, this is not very deep result or anything, but anyway it requires little bit of work. So, we will see the proof of this in the next lecture. So, I will stop here. Thanks.